Welcome everybody to this talk. I would like to begin with thanking the organizers of the virtual Gromov Birthday Conference 2020 for having me give a plenary talk in honor of Mrs. Gromov's birthday. And then I'd like to continue with saying happy birthday to Mrs. Gromov. My talk will be on explicit minimizing sequences related to the Riemannian Penrose Inequality and Bartnik's mass function. And use the structure of my talk. In the first video, I'll give first the setup and definitions that I'll work in and work with, and then I'll talk about the result and its context. Part 1, the Riemannian Penrose Inequality. That's the context, not the result. In video 2, part 2 of the talk, I'll talk about the second part of the context of result and also about ideas for its proof, based on the mental Lewis chain construction that I'll explain. And in the third part, we'll delve a little deeper into the result and into its proof. And this is joint work with Armando Pacheco from Tübingen. And for those of you looking for interesting problems to work on related to the project I'm describing here, I'll mention some open problems at the end of this video, this first video, at the end of part 1. So let's begin with the setup and definitions. We keep working in a three-dimensional smooth Riemannian manifold, and we assume that it has possibly non-empty boundary, and the boundary is always going to be part of the manifold. I assume the manifold to be geodesically complete all the way down to the boundary, and to have non-negative scalar curvature. These properties are going to be satisfied by all manifolds except some limits. And they're also all going to be asymptotically flat in the sense that the manifold consists of, outside some compact set, consists of a region which is diffeomorphic to R3 outside some closed ball, which gives me coordinates x1, x2, x3 to work with on this exterior region of the compact set, and a coordinate radius, the formula of which you can see here. As you would expect from Euclidean space, and this is going to be playing the role of a coordinate radius. And in this coordinate chart, outside the compact set, the components of the metric gamma, gamma ij, will look like delta ij plus lower order terms as r goes to infinity, where delta ij are the components of the Euclidean metric or the Kronecker delta fluid. For the experts among you, the lower order terms are characterized as OK of 1 over r to the power q, where q is some real number bigger than 1/2, and k is a natural number bigger than 2. And this can be worded also in weighted CK or Sobolev spaces, and the k for the non-expert means that this description as the metric looking like delta ij plus lower order terms continues to hold up to k derivative, with the lower order terms being adjusted appropriately. And in this setup, there's a well-defined notion of mass, that's a physical name, which is a real number associated with this manifold in gamma, which is called the ADM mass, where A, D, and M stand for Arnold Design-Misner, a notion from the 1960s, about which we by now know many things. And the most famous thing maybe that we know about this mass is that it is the mass featuring in the Riemannian positive mass theorem that was proved by Shen and Yao and by Witten in the early 1980s. And it states the following: if we have a smooth Riemannian manifold which is geodesically complete, now without boundary, asymptotically flat, and has non-negative scalar curvature, then its ADM mass is non-negative, and equality holds in this inequality if and only if the manifold is globally asymmetric to completely flat Euclidean space. This is a very deep result which has stimulated many generalizations, refinements, and applications, both in geometric analysis and mathematical relativity. Now, our setting is not this fully geodesically complete setting, but instead we do have an inner boundary in our setting, which is diffeomorphic to S2, and we'll denote the induced metric by G. This boundary sitting inside our 3 manifold will be a minimal surface in the sense that the mean curvature H is going to vanish. And also we will require that it is strictly outward minimizing in the sense that its area strictly less than the area of any other two surface which is homologous and sits inside the free manifold. And we'll also briefly use the notion of being weakly auto-minimizing, where the strictly less than becomes less than or equal to in this area comparison. It is known that being strictly out-minimizing for a minimal boundary implies that this boundary is strictly stable, while weakly out-minimizing implies being weakly stable in the sense of variation of area. So much for the setup. And here's the prime and most important example for our setup, and that's the so-called spatial Schwarzschild manifold, and I'll drop the qualifier spatial in what follows. So that manifold is defined on the exterior region of a given ball in R3 directly, so we don't need any diffeomorphisms here. And the ball has a radius 2m, where m is a positive real parameter called the mass parameter, and the metric is going to be given by the formula that is shown on this slide. And you can see that as r equals 2m, this degenerates, which is why we have to take out the boundary as well. And it's also spherically symmetric. It doesn't depend on any of the angles in R3. And G star denotes the canonical metric on S2. In this example, the boundary is the two-sphere in this R3 of radius 2m around the origin. So it is topologically a two-sphere. And it is actually round with induced metric 4m squared G star, which leads us to having an area of the boundary of 16 pi n squared, which is a number that will be relevant again in a second. The Schwarzschild manifold has vanishing scalar curvature, and it's asymptotically flat, with ADM mass being exactly this parameter m in the metric. So in particular, it's positive. Moreover, this boundary as sitting inside our Schwarzschild manifold is minimal and strictly out-minimizing. And I told you to remember that the area of the boundary with respect to the induced metric G is 16 pi m squared. And actually what I would like you to remember even better is this equivalent reformulation, which might look a little bit awkward if you've never seen it before, that the square root of the area of the boundary with respect to the induced metric divided by 16 pi actually equals this number m, which is the parameter of the Schwarzschild manifold, which, recall, I said can be computed to be the same thing as the ADM mass of this metric and is positive. And this equivalent reformulation I would like you to remember. There's a physical interpretation of this whole manifold Schwarzschild example. It models a static, isolated black hole in vacuum, of course spherically symmetric, at some instant of time, and the boundary of M is then modeling the horizon of this black hole. And this identity that I just derived by simple computation between the mass and the area of the boundary of the horizon can then be interpreted as saying that the mass of the black hole horizon, which is the square root on the left-hand side, equals the ADM mass, which is interpreted physically as the total mass of this gravitating system in the context of general relativity. This is, in this example, we have this identity. And maybe the physical interpretation is not so relevant for everybody or not so interesting, but it's a useful guideline to understand what's coming. You may have noticed that the metric degenerates. I'll show you the formula again. The metric degenerates the Schwarzschild metric at r equals 2m. And in the statement of the setup I'm working with, I said that the boundary should always be a subset of the manifold. So we have a problem here, but it's well known that this problem can be removed by changing this radial coordinate appropriately, and we'll actually see how this is being done in part 2 of the talk, or one of the versions in which this can be achieved. And then the metric actually does smoothly extend to the boundary, just the coordinate r does not. So you can trust me that all the things I've said above are fine. It's just not so straightforward to check them in this coordinate system. Okay, so we've now seen this identity between the mass of the Schwarzschild black hole horizon and the total mass of the Schwarzschild system. And in fact, there's a much deeper result called the Riemannian Penrose Inequality that I would like to go into now, which is related to this identity. The Riemannian Penrose Inequality was, of course, conjectured by Penrose and then proved in the early 1990s by Gray and by Huskell and Ilmanen, and Huskell and Ilmanen used inverse mean curvature flow ideas going back to Gavotch. And it can be considered as a refinement of the Riemannian positive mass theorem that we've seen above. And the context here is exactly the context I described. We have a smooth Riemannian manifold with non-empty boundary. The boundary should be minimal and strictly auto-minimizing. The manifold should be asymptotically flat, have non-negative scalar curvature, and be geodesically complete up to the boundary. And in that case, the square root of the area over 16 pi, which is the notion you've seen before, and that before I called the mass of the black hole horizon, is always less than or equal to the ADM mass of the whole manifold, with equality if and only if it's isometric to the Schwarzschild manifold of mass m, being this ADM mass. So we knew already that Schwarzschild saturates this inequality, and this rigidity statement now says that actually it's the only manifold up to isometry which saturates it, or the only one parameter from the manifold. This is the famous Riemannian Penrose inequality from geometric analysis and or mathematical relativity, as you will. And also, this theorem has stimulated many refinements and applications and generalizations that I won't have time to go into. Some I will go into. Now we have all the ingredients together to where the theorem I would like to talk about today. And this is by Cabrera-Pacheco and myself from this year. And it goes as follows. Let G0 be some smooth Riemannian metric on S2 with best eigenvalue of the following operator minus Laplacian on G0 plus k G0, where k is the Gaussian curvature. It has to be strictly positive. Give me such a metric, please. Then there exists a sequence of smooth Riemannian metrics gamma k on the manifold M, which is 0, infinity plus S2. So you can imagine the manifold as being a cylinder, such that the boundary for OK, we have all the properties we want, as I described before, namely the boundary, which is 0 plus S2, and I'm going to just identify it with S2 from now on. Fits inside M gamma k as a minimal outward minimized, strictly outer minimizing surface. Surface. Moreover, the scalar curvature of each gamma k is non-negative, and it's geodesically complete up to the boundary. And there exists a number sk bigger than 0, such that gamma k is restricted to the part of the manifold sitting outside this parameter is isometric to the Schwarzschild metric of some mass mk, which is positive, outside some ball of radius rk, which is bigger than 2nk. So we're really inside the bulk of the Schwarzschild manifold. And this implies, as we discussed before, that gamma k is asymptotically flat with the mass of gamma of m with respect to gamma k being mk. Okay, so let me repeat. We have this G naught that you give me as a metric on S2, which has this property that the first eigenvalue of this operator is strictly positive. And then I tell you there exists a sequence of smooth Riemannian metrics on this cylindrical manifold that looks like 0 infinity with 0 included plus S2, such that each metric in the sequence makes the boundary into a strictly outward minimizing minimal surface. Each member of the sequence has non-negative scalar curvature and is geodesically complete up to the inner boundary. And for each metric, there exists a number in this interval 0 to infinity, such that if I restrict the metric to the outer part outside this SK, actually I'm identical to the Schwarzschild metric, with the Schwarzschild manifold of some positive mass outside some ball. So I'm not going all the way down to the horizon in the Schwarzschild, but I'm staying outside. So in particular, gamma k is asymptotically flat with ADM mass mk. And these numbers, furthermore, these numbers mk converge from above to a number m infinity, which is still positive, and which turns out to be the area of this boundary with respect to my given metric G0 divided by 16 pi. The scale goes to infinity. And moreover, on this manifold, these metrics converge to the metric gamma infinity in the C1 alpha topology on compact subsets. Where alpha is any number strictly between 0 and 1. And you know gamma infinity precisely. Gamma infinity is C11 globally, not C2. Gamma infinity on M without some S infinity cross S2 is C infinity. Gamma infinity restricted to S infinity infinity is isometric to Schwarzschild with mass m infinity. And this time all the way down to the horizon. And of course, the SKs converge to S infinity. SK goes to infinity. Anything else? Yes, of course. The boundary sitting inside gamma infinity is minimal, not only weakly outer minimizing. And furthermore, G infinity, the induced metric on the boundary from this metric G gamma infinity is G0, or isometric to G0. And in particular, gamma infinity is not isometric to Schwarzschild. Not to any, but in particular not to the one of mass m infinity. Yet, this expression that you have seen before, the area of the boundary of m with respect to g infinity, which was g0, divided by 16 pi, take the square root, equals m infinity. Okay, so before I say anything about what this means, let me make a big sketch. So for gamma k, I have s here, starting at 0 and going out to infinity. Okay. And so I'm given this metric 1 is 2, which I call G0, and then from it we construct a neck-like manifold, which becomes spherically symmetric after some parameter. Opens up. And then eventually, after some parameter sk, it will look like a piece of Schwarzschild of mass nk. And it has a positive scalar curvature all throughout this picture. And then as k tends to infinity, we have the same manifold, so I draw into the same picture. We start out with the same metric on the initial surface. And then I'll keep the color scheme for you to identify the portions, but of course the places where things happen are not the same S's, same parameters. Then we have some kind of a cylindrical manifold here, which at some point becomes spherically symmetric. And then after that, it ends at some surface at parameter value s infinity, from which on it's Schwarzschild starting with the minimal surface of mass m infinity. Okay, so that's what the limit looks like, and all these have non-negative scalar curvature. This s infinity surface, s equals s infinity surface, is not smooth inside this 3 manifold, but it's a C11 regular C2, not C2 cross section. And this S infinity surface is actually strictly outward minimizing in this limit manifold gamma infinity. So what does this mean that we have this sequence? So one thing it means is the limit, as you can see in the identity at the top of the slide, the limit saturates the Penrose inequality. The Riemannian Penrose inequality is saturated by the limit gamma infinity. Yet the limit is not isometric to Schwarzschild, only outside some piece. And behind that piece, there is still some, in some sense, cylindrical portion where it's not isometric to Schwarzschild because Schwarzschild doesn't have that cylindrical portion. Okay, so we have a saturating manifold, and it does not contradict the rigidity case of the Riemannian Penrose inequality, of course, because it is not smooth, and the inner boundary indicated here by G0 is not strictly outer minimizing. So there are two assumptions of the Riemannian Penrose inequality rigidity statement that are not satisfied by gamma infinity. So gamma infinity saturating the Riemannian Penrose inequality doesn't contradict the rigidity statement, obviously. It should be possible to contradict. Okay, so in some sense, this problem, so the cylinder in the limit hides behind the surface at s equals s infinity, in the sense that s equals s infinity is an outward minimizing minimal surface inside this manifold with metric gamma infinity. And this is what physicists would call an outermost horizon. So from the perspective of an observer far away, who looks from the outside, so from the infinity, all the business that looks weird, namely the cylinder in the lower picture, hides behind this outermost horizon and somehow doesn't seem to be visible from outside the horizon. because it's behind the horizon. Okay, so in some sense we can describe the sequence and its limit that we found as a type of instability of the Riemannian Penrose inequality. We've got a sequence of manifolds that almost saturate the Riemannian Penrose inequality, limiting to something that saturates it, but it does not converge to the case of rigidity worded in the theorem. So in that sense, we have a C1 alpha on compact sets instability here. Yeah. But it hides behind the outermost horizon, which is important. Let me mention that the C1 alpha on compact subsets convergence. Implies convergence in a lot of topologies. For example, in Gromov-Hausdorff convergence in topology, and in Somani-Wenger intrinsic flat convergence. Intrinsic flat distance. Intrinsic flat distance. Which follows from a work by and again in alphabetical order, Allen, Curvature, Lansman Huang, Sajat Laxian, Dan Lee, Raquel Perales, and Christina Somani, and of course Stefan Wenger as well. Okay, so we have not only a C1 alpha instability, but also as a consequence of Gromov-Hausdorff and Somani-Wenger intrinsic flat instability. Actually, in Somani-Wenger intrinsic flat distance, a similar instability was already known due to work by Lee and Somani, 2012, I believe. Already discovered an instability in the sense of the Riemannian Penrose inequality in spherical symmetry, and the limit space they obtain looks very similar to the ones I just drew. It's a round cylinder in this case because of the spherically symmetric scenario, joined directly by a Schwarzschild at the horizon. So this is also a Schwarzschild of some mass positive, and they can construct limits that have any length of cylinder hiding behind the Schwarzschild. And their limits look very similar to ours, and actually in the spherically symmetric case of our metric G0 is spherically symmetric, the limit we get looks exactly like theirs, and we can also determine the length of this limit. So we recover their result in the spherically symmetric scenario, but extend it beyond spherical symmetry for this given emission metric G0, which had this positive eigenvalue condition, and their result is in Somani-Wenger intrinsic flat distance. Okay, and it uses the concept of integral current spaces. Another result I would like to relate our result to is the result by Brian Allen from 2018. Who proves stability, in this case, of the Riemannian Penrose inequality under an assumption, which is that the piece of the manifold he looks at is uniformly foliated by a smooth inverse mean curvature flow. recall, I mentioned it very briefly, the proof of Huisken and Illman of the Riemannian Penrose inequality and its rigidity statement uses weak inverse mean curvature flow. Here we have smooth inverse mean curvature flow, so it's an assumption to begin with that a member of a sequence of Riemannian manifolds has a smooth inverse mean curvature flow. And there's an additional assumption that along the sequence of manifolds considered, this inverse mean curvature flow is uniform. And in that case, he obtains stability in an L2 sense. And you may now wonder, and we have wondered, what happens along our sequences? Do they have a smooth inverse mean curvature flow to begin with? And if so, is it uniform? Or why is it not uniform? Because then it would contradict the result by Brian Allen. So it turns out that the S levels, where the surfaces S cross S2, are the leaves of smooth inverse mean curvature flow starting at the horizon in our examples. Smooth inverse mean curvature flow in gamma infinity, sorry, not gamma infinity, gamma k. But they're not uniform. Not uniform in k. And why not? I can show best in the picture. So we go back into the picture of our converging members of the sequence. Then all these S cross sections now that look vertical more or less in my picture have are leaves of a smooth inverse mean curvature flow in the metric gamma k depicted here. And they have some mean curvature. And this mean curvature, if you are behind this Sk, from the perspective of S equals infinity, then this will shrink to zero, to zero mean curvature. All the S equals constant spheres in the cylindrical part of the limit of the gamma infinity in the lower picture, they all have mean curvature 0. Okay, so this mean curvature cannot be uniformly controlled. And I'm glossing over the detail here that Sk, of course, is not equal to S infinity, but converges to S infinity, but the idea remains the same. So all these S equals constant surfaces have positive, not necessarily constant mean curvature in the gamma k's, but these mean curvatures converge to 0 if you're behind this outermost horizon in the limit. So they cannot be uniformly bounded in their mean curvature away from 0. So in that sense, our manifolds gamma k do have smooth inverse mean curvature flows, but those cannot be uniformly controlled in the sense that Brian Allen discusses. So the result by Allen is not, of course, not contradicted and completely consistent. And you can see in our example somehow why he needs this uniformity in the inverse mean curvature flow, and that this cannot easily be discussed away. In the paper I mentioned already by Lee and Sormani, there's also a positive source stability result in spherical symmetry for the Riemannian Penrose inequality in spherical symmetry. Of course, under some assumptions that I can't explain here. And with respect to Sormani-Wenger intrinsic flat distance. And of course, in case we choose the G0 to be round and start our construction in this round way, we will get a spherically symmetric metric as well. So we get another example for the instability they discovered, but also in the parts of the manifolds where their result holds, it turns out to become the part of the manifold outside the outermost horizon in the limit. So it also is nicely and sweetly consistent with their result. I want to make two more remarks on our result and its context. One is that this instability that Lee and Sormani discovered and that we generalized beyond spherical symmetry may be relevant for the discussion of the stability of the positive mass theorem, as is explained in Lee and Sormani's paper from 2014 on the stability of the positive mass theorem, where they conjecture when it possibly may be stable and unstable. Positive mass theorem. And whoever is interested in this stability and instability problems, I would love to refer to Christina Sormani's video on YouTube from the Simon Center conference, and the link will be in the text of the description of my video. And of course, I don't know when in the future you will actually watch this talk, so Christina Sormani's talk, of course, only then gives the state of the art of when the talk was. And there may be new results by the time you watch my video. And even actually between her talk and now, there may be new results that I'm not aware of. More importantly, for the rest of my talk, I would like to mention that there was another work by Mantelidis and Shane in 2015. Discussing somehow indirectly the stability of the positive, the Penrose inequality. And I will talk more about this in part 2 of the video. So they discovered an indication of the instability we discuss here. Instability, and I'll say more about this, as I said, in part 2. But I do not want to end this first video without saying that we heavily rely in our proof on ideas by Mantelidis Shane. Well, I'll even write used here a lot. And of course, we also rely on other people's work that I do not want to skip in the first video. And so they prove refinements of these constructions and generalizations to various other contexts. And I again put them in alphabetic order. So this would be Curvature, Pacheco, himself, Bartnik, Miao, and Xu. So these people prove refinements in various combinations of authors, refinements of this construction by Mantelidis and Shane. I'll say more about this in the second and the third video. And we rely on some of the techniques developed in those refinements as well. Last but not least, our result also has some implications for Bartnik's mass functional, as the title of the talk indicates, but considering the audience of this conference, I decided to skip that entirely, and I refer you to the upcoming paper for this. So before I end this part of the talk, let me mention the open problems I promised you. And I'm not claiming that I'm working on any of those, neither is my co-author, so we'll be happy if you want to work on that. And feel free to contact us if you want to collaborate. So one is, all of them are construct similar sequences and hence discover similar instabilities in various other scenarios. One scenario is consider manifolds of dimension n bigger than 3, and this would be related to work by Gray and Lee from 2009 about the higher dimensional Penrose inequality, and by Curvature, Pacheco, Miao, in 15 about high-dimensional analogs or generalizations of the mentally the same construction and results. Then instead or in addition, so in n equals 3 and also in n bigger than 3, it would be interesting to look not only at asymptotically flat scenarios with Schwarzschild as your guiding example, but at asymptotically hyperbolic Riemannian manifolds with Schwarzschild ABS as your example. That should guide you, and this would be related to work by Chico and Sakovic from 13, also from Rosio from 15, and De Lima and Girao from 16 on all three of them on aspects of the asymptotically hyperbolic analog of the Riemannian Penrose Inequality, and to work by Cabrera and Chekhov, myself and McCormick from 18 on an asymptotically hyperbolic analog for n equals 3 of the mentally the same construction, and also Cabrera, Pacheco, and myself, and Penuela and Gearing, and Penuela in preparation about the asymptotically hyperbolic case in general dimension. And also for n equals 3 and n bigger than 3, it would be interesting to study the electrically charged situation, which is relevant for the physics of electrically charged black holes and manifolds. And this would be related to work by Visconti and Corey from 12, building on work by Zhang 79 on the electrically charged Penrose inequality, and on work by Orai and Kanga and Cabrera Pacheco, and myself on the n equals 3 generalization of the mentally the same construction to this electrically charged context, and to this paper as well by Cabrera Pacheco, myself, Gearing, and Penuela in preparation about the higher dimensional analog of the mentally the same construction in the electrically charged context. I'd like to end the first video here, and would like to thank you very much for your attention, and I hope to see you soon again in the second video.